Imagine standing on the surface of Mars. No spacesuit, just you and the planet. In the first 10 seconds, 3 things happen simultaneously. The near-vacuum atmosphere causes the moisture in your eyes, mouth, and lungs to boil. Not from heat, but from the absence of pressure. Your blood begins to bubble beneath your skin, and the temperature, a brutal minus 60 degrees Celsius on an average day, begins freezing what's left. You'd be unconscious in about 15 seconds, dead in under a minute. And this is the planet we're planning to colonize. We talk about Mars like it's the next frontier, the backup plan for humanity. Billionaires race to build rockets, agencies draft mission timelines, and the public imagination has already furnished Martian habitats with greenhouses and sunrise views. But here's what most people miss. Mars isn't just hard to get to. Mars is actively, relentlessly hostile to human life in ways that make it arguably the most dangerous destination we've ever seriously considered. And the deeper you look, the worse it gets. So let's look. Let's take Mars seriously, not as a dream, but as a real place with real physics. And let's ask a question that doesn't get asked enough. Should we actually go? To understand why Mars is so terrifying, you first need to calibrate your sense of scale. Mars sits an average of about 225 million kilometers from Earth. But as we covered in a previous video, that distance constantly changes. At its closest, during opposition, Mars is roughly 55 million kilometers away. At its farthest, over 400 million. Even at the minimum distance, in a car driving non-stop at 100 kilometers per hour, you'd arrive in about 60 years. But distance isn't really the problem. The problem is what's waiting on the other end. Let's start with something you'd notice the moment you stepped outside: the atmosphere. Or more accurately, the almost complete absence of one. Mars has an atmosphere, technically, but it's less than 1% the density of Earth's. On Earth, atmospheric pressure at sea level is about 1,013 millibars. On Mars, it averages around 6. That's not thin air. That's essentially a vacuum by any human standard. Your lungs wouldn't just struggle. They physically cannot extract oxygen from that environment. And even if they could, there's almost none to extract. The Martian atmosphere is about 95% carbon dioxide. Oxygen makes up roughly 0.13%. For reference, Earth's atmosphere is 21% oxygen. You're not breathing on Mars. You're suffocating in a sea of CO2 while your body depressurizes. Now here's the part people overlook. This thin atmosphere doesn't just mean you can't breathe. It means Mars has virtually no protection from radiation. On Earth, our thick atmosphere and magnetic field form a double shield against cosmic rays and solar radiation. Mars lost its global magnetic field roughly 4 billion years ago when its core cooled and solidified. Without that magnetic dynamo, the solar wind slowly stripped away the atmosphere over hundreds of millions of years. What remains offers almost no radiation shielding. The surface of Mars is bombarded daily by galactic cosmic rays and solar particle events. An astronaut on Mars would absorb radiation at a rate roughly 40 to 50 times higher than on Earth's surface. Over the course of a 2 to 3 year mission, which is the minimum for a Mars round trip, that cumulative dose would likely exceed NASA's current career limits for astronauts. We're talking about a measurable increase in cancer risk,
potential cognitive decline, damage to the central nervous system, and accelerated cardiovascular aging.
And here's the catch: you can't just hide from it. Cosmic rays are so energetic that they penetrate most conventional shielding materials. Worse, when these particles hit metal walls, they produce secondary radiation, a shower of additional particles that can be even more damaging than the original rays. Thicker walls don't always help. Sometimes they make it worse. The radiation on Mars isn't an engineering inconvenience. It's a fundamental threat that we currently have no reliable solution for. But let's say you've found shelter. You're inside a habitat, pressurized, oxygenated, shielded as best you can manage. You're safe now, right? Not quite, because the ground beneath your feet is trying to kill you too. Martian soil, known as regolith, contains high concentrations of perchlorates. These are toxic chemical compounds that on Earth are classified as hazardous. Perchlorates interfere with thyroid function, disrupting the hormones that regulate metabolism, growth, and development. Mars regolith isn't just barren, it's chemically hostile to biology. Any food grown in Martian soil would need extensive processing to remove these toxins. Any dust that enters a habitat, and dust will enter, because Martian dust is incredibly fine and gets everywhere, becomes a health hazard. And that dust does more than contaminate, it destroys. Mars experiences planet-wide dust storms that can last for months. In 2018, a global dust storm engulfed the entire planet for nearly 2 months. It was this storm that killed NASA's Opportunity rover by blocking sunlight from reaching its solar panels. The dust particles are extremely fine, smaller than a human red blood cell, and carry an electrostatic charge. They cling to everything: solar panels, visors, seals, filters, mechanical joints. Over time, they degrade every system they touch. If your power generation depends on solar energy, a single major dust storm could cut your output by over 90%. And Mars averages 1 to 2 regional dust storms per year, with global storms occurring roughly every few Martian years. Think about that. You're on a planet where the weather can, without warning, cut your power supply for weeks. And you're 55 million kilometers from the nearest help. Now zoom out for a moment. We've talked about the atmosphere, the radiation, the soil, and the storms. Each of these is a serious threat on its own, but they don't exist in isolation. They compound, they interact, and they create a cascading risk environment that is fundamentally different from anything we've engineered for before. Consider what happens when a dust storm reduces solar power. Your habitat's life support runs on that power. CO2 scrubbers, water recyclers, heating systems, all of them need energy. If power drops, you start rationing. If rationing fails, systems begin shutting down. Temperature drops, CO2 builds up. And you're doing all of this while absorbing radiation with no way to call for help in real time, because a signal from Mars to Earth takes between 4 and 24 minutes, depending on orbital positions. There's no mission control rescue, there's no emergency resupply, there's no abort. On the International Space Station, astronauts are 400 kilometers above Earth. If something goes catastrophically wrong, they can be home in hours. On Mars, the nearest return window is months away. And that's if you have a functioning return vehicle, enough fuel, and a body that can survive the trip back.
Let's talk about what Mars does to the human body. And this is where the argument against going becomes almost impossible to ignore. We covered this in depth in a previous video about why Mars astronauts probably can't return to Earth. But it bears repeating here because the implications are staggering. The journey alone takes 6 to 9 months in microgravity. During that time, astronauts lose 1 to 3% of their bone mass per month. Muscles atrophy at a similar rate. The heart, no longer pumping against full gravity, begins to shrink. Blood volume decreases. The immune system weakens. Vision deteriorates as intracranial pressure shifts fluid toward the head, physically deforming the eyeball. After 6 months on the ISS, astronauts often can't walk unassisted when they return to Earth. And that's after half a year. A Mars mission lasts at least 2 to 3 years. When astronauts finally arrive on Mars, they step into 38% of Earth's gravity. That's better than 0, but likely not enough to halt the deterioration. Models suggest that Martian gravity is insufficient to maintain Earth-adapted bone density and muscle mass over extended periods. The body continues to weaken. After a year or more on Mars, followed by another 6 to 9 months of weightlessness on the return trip, the astronaut arriving back on Earth would have the skeletal structure of someone with severe osteoporosis. Standing up could fracture a hip. Walking could break a leg. The heart, shrunken and deconditioned, would struggle to pump blood against full gravity. Some researchers believe that after a full Mars mission cycle, the body may never fully recover. This isn't speculation. This is extrapolation from decades of data collected on the ISS. The science points in one direction. Going to Mars may mean never being able to come home. Not because we lack the rockets, but because the human body won't survive the return. And then there's the mind. Psychological studies of isolated, confined environments consistently show that even carefully selected, rigorously trained individuals begin to deteriorate psychologically after extended periods. Depression, anxiety, interpersonal conflict, cognitive decline, all documented in Antarctic research stations, submarine deployments, and ISS missions. And those environments all have one critical safety net: an exit. You can be evacuated. You can abort. You know that Earth is reachable. On Mars, there is no exit. The next launch window home is over 2 years away. If a crew member has a psychological breakdown, there is no hospital, no therapist's office, no walk in the park. There is a metal box, a handful of other humans you didn't choose, and 55 million kilometers of empty space between you and everyone you've ever known. The communication delay means you can't even have a real conversation with loved ones. Every message is a monologue sent into the void, answered minutes or hours later. Isolation studies on Earth, like the Mars 500 experiment, showed significant psychological strain, even in simulated conditions where participants knew they could leave at any time. Remove that option entirely, and the psychological risks become profound. So let's lay it out clearly. Mars has no breathable air. Its atmospheric pressure would cause your bodily fluids to boil. The average surface temperature is -60 degrees Celsius, dropping to -120 at the poles. The soil is toxic. The dust is destructive and pervasive. There is no magnetic field, and thus no meaningful radiation protection. The planet experiences global storms that can last months. The journey there and back devastates the human body. And the psychological toll of permanent isolation on an alien world is largely unknown, but almost certainly severe.
This is the planet we're racing to send people to. Now, to be fair, none of this means Mars exploration is worthless. Robotic missions have been extraordinarily successful. Perseverance,
Curiosity? Insight? These missions have taught us about Martian geology, climate history, and the potential for ancient microbial life. We can continue learning from Mars without putting human lives in a situation where every single system, biological, mechanical, and psychological, is operating at the extreme edge of failure. The counter-argument is always that humanity needs a backup planet, that we need to become multiplanetary to survive extinction-level events. And there's a certain logic to that. But it's worth asking whether Mars is actually that backup. A world where you can't breathe, can't grow food without extensive processing, can't go outside without a pressure suit, can't shield yourself from radiation, and can't maintain your own body's structural integrity. That's not a backup. That's a survival scenario with no clear endgame. Some scientists have proposed terraforming, gradually transforming Mars into a more Earth-like world. But the timescales involved are measured in centuries at minimum, more realistically in millennia, and the feasibility is deeply uncertain. Mars doesn't have enough CO2 locked in its ice caps and soil to meaningfully thicken the atmosphere, even if we released all of it. Without a magnetic field, the solar wind would continue stripping away whatever atmosphere we build. Terraforming Mars isn't a plan. It's a hope, and a distant one at that. The deeper problem is this: we evolved for Earth. Every cell in our bodies, every organ, every biochemical process is tuned to this planet's gravity, atmosphere, magnetic protection, and radiation environment. We are not general-purpose organisms. We are Earth organisms. And Mars is about as far from Earth's conditions as you can get while still having a solid surface to stand on. There's a certain poetry in our obsession with Mars. It speaks to something fundamental about us, the refusal to accept limits, the drive to explore, the need to know what lies beyond the horizon. These are admirable qualities. They've taken us from caves to continents to the moon. But there's also wisdom in recognizing when the horizon is a wall, when the physics isn't a challenge to be overcome, but a reality to be respected. Mars isn't a frontier waiting to be tamed. It's a graveyard with a sunset. Perhaps the bravest thing we can do isn't sending humans to Mars. Perhaps it's continuing to send our machines, our telescopes, our rovers, and our curiosity, while keeping our fragile, beautiful, Earth-adapted bodies right where they belong. On the only planet in the known universe where we can walk outside, breathe deeply, feel the rain, and look up at Mars in the night sky, safely from a distance of 55 million kilometers. I hope you enjoyed the video. If you did, a like and a subscribe would really help the channel. I'll see you next time.